So we have y equals e to x plus 2 minus 3. Yes? That's the one. Okay, so now remember, e is a number greater than 1 or less than 1. If you say greater than 1, the function will look like this. If you say less than 1, the function will look like this. Which one? Is e a number greater than 1 or smaller than 1? Okay, we don't know. That's okay. So let's go to the calculator. Here is e, the division symbol, second and e, and just press enter. I'm sorry, let me show again. So second, division symbol, and press enter. So e is 2.71828, etc., etc., etc. So is it a number greater than 1 or less than 1? Right, so then the function is going to be increasing. We'll have a horizontal asymptote at negative infinity only, and it will blow up. We say it will go to infinity. It's the fastest possible growth. Good. This is going to take some time from the lecture. It's not quick. Okay, so when we graph the base function used here, we graph e to the x. Yep, I got it. We graph e to the x, which is increasing on all its domain as we discussed. I hope it's not me.
I'm sorry, I thought I turned the sound off.
It will always cross, the pure exponential function will always cross when x is 0, y is, thank you very much. So the pure exponential function will always cross. If it's decreasing or increasing, it doesn't matter. It will always cross the y-axis at 0, 1, the pure exponential function. The first step in order of transformations here would be what? Excellent. So the first transformation is e to x plus 2 left 2 units. So this point, can anyone give us, this is my reference point. Where will this point go if the whole graph moves to the left 2 units? So obviously it will go at the point
-2.
Excellent, -2, 1. So this is e to x plus 2. Notice that the horizontal asymptote did not change. So this is still the horizontal asymptote. I should have written this, but it's everywhere, but it's specifically on the left-hand side, right? I cannot just graph a line, a horizontal line, just this little piece. I have to graph the whole thing. So when a function has a horizontal asymptote and we shift it left and right, the horizontal asymptote doesn't change. But what happens if I shift this graph up or down if it has a horizontal asymptote? What will happen first? What will I have to graph first? Shift the asymptote. Awesome. Okay, so then in step number 2, this is a transformation on number 1. So this will be e to x plus 2 minus 3. Where does this graph go? What transformation is this on this? Down 3. I can't shift it down 3 before I shift the horizontal asymptote. Where will I shift it to? Very good. So this is y equals -3. Now I want my reference point, this one. Where does it go?
-2, -2.
Very good, awesome, thank you. Now, I have no idea where this will cross. It may cross the y-axis below x-axis, it may cross above. I have no idea. I don't know. I can determine though. +2 minus 3. So let's find, since we are here, I would like to find the x-intercept algebraically and the Y-intercept algebraically. How do I find the x-intercept for any function?
Set y to 0.
Of course, perfect. How do I find the y-intercept for any function? Perfect, excellent, thank you. So in order to solve this, I have e to x plus 2 minus 3 equals 0. In order to determine this, I have to find f of 0, which is e to 2 to the second power e squared minus 3. And then I'll go back and I'll adjust my graph once I find these. So let's start with the easy one. So this is 2.7 squared minus 3. Obviously it's going to be a positive number. So as I was expecting, the y-intercept will be above the x-axis. So let's find that. So e squared. Let me know if you want me to show, because it will take like forever if I do. Squared minus 3. So that is 4.4 approximately. So 0, 4.4. So obviously the y-intercept is above the x-axis. Now for the other one, how do I solve this and what type of equation is it?
Natural log?
Yes, so it is an exponential equation. Awesome. Exponential. Why is it exponential equation? Because the variable is at the exponent level. So then we have e to x plus 2. First of all, we have to separate it. We can apply log to a difference. So if you remember the rules of log, we only have 3 actually. If you want me to refresh your memory and write them down, I will. Log applied to a product, log applied to a ratio, and log applied to a power. So if I apply log to both sides as is, first of all, I'm not going to be able to do anything to this, and I can never apply log to 0. It would be an error. Remember the graph of log, or natural log. This is the graph of natural log. Crossing at 1, 0, this is natural log x. So I can never plug in 0. X equals 0 is a vertical asymptote. So I will never be able to apply log to this number. But once I separate them, I separate the expression that has x in it and from the free term, if you want, or 3 in this case. Now I can apply natural log to both sides and solve. And I will do that in a second. My question is again, do I need to show those 3 properties of log? Yes or no?
Yes.
Okay, perfect. So we have 3 properties. No, we don't. Log has. So log in any base of a product. I didn't put any base. So if I don't put a base, it's base 10. But let me put any base so you understand it. It works for 10 and e and anything. So this is log a plus log b. In any base. It can be natural log, it can be base 10, common log, it can be any base. Is this clear or a little fuzzy? Okay. The one with the quotient is identical but with minus. And these properties have to be understood in a dynamic way, meaning if I'm given this, I can condense like that. If I'm given that, I can expand like this. So back and forth, they work from either direction. And the last one, and I'm also going to show you the change of base formula. And the last one is log base a of a raised to a power, let's say b. B becomes a factor in front, goes in front as a factor. When I say factor, means it multiplies log. And the change of base formula, I'm looking to the side to see sometimes my video stops or it happened. Rarely, but it happened. So the change of base if I want to determine, let's say, log base a of x, some calculators will allow you to put the base you want. That's fine. Some calculators will not. I have an old calculator that does not give me the option of putting the base I want. So we can use one of the two bases that almost all calculators have, log of x of a log of the previous base. So this is a ratio of logs, not to be confused with log applied to a ratio. This is log x over log a, and when we do not write the base is 10, common log. And the other option is this. Both have to be base e, both have to be base 10, and this is a ratio of two logs, not log applied to a ratio. Is that okay? So coming back to our equation, yes, Hannah is right, she said apply log, yes. So, and she was also correct, the best log to apply here is natural log because this is base e. So if two numbers are equal, their logs in the same base will be equal to each other. So remember the factor, it's x plus 2. I should put in parentheses times natural log e. Let me do it just this time. But does anyone remember how much is natural log e? 1. So if, in case you don't remember, you can put in the calculator, or I can show you the property. Here's the property. What is the base here? I don't see a base. If it's ln, the base is e, but we don't write it by convention. E raised to which power is e? E raised to which power counterclockwise is e? And that's why the answer is 1. So since this is 1, then we have x equals, I move 2 to the other side, negative 2 plus natural log 3. I prefer not writing anything after natural log if I can avoid it, and also after a square root if I can avoid it. So now we will put in the graphing calculator. Let's determine what this is. So natural log 3. Let me know if you want me to switch. Minus 2, please do, okay? So I got negative 0.9. So the approximate x is negative 0.9. So the ordered pair is negative 0.9 comma 0. So knowing that, I can now go back and come up with a better graph. So here it is. I know it crosses at, what was it, 4.4. So it crosses here. It has a horizontal asymptote at negative 3. And it's at negative 0.9. So this is a much better graph than the one from before, because I determined the X and Y-intercepts algebraically. So this is the function f of x or y e to x plus 2 minus 3. How are we doing so far? Now all these functions are, yes, thank you. All these functions are needed for this course. Perfect. Moving on. The next one, do we need to graph the next one, or is it known? Let's find the domain. So how do I find the domain of this function? What do I have to write? We had an example last time when we determined the domain, so yes, please, Mason. I'm sorry? Only if, excellent. Only if it's a non-linear inequality. If it's a linear inequality, I don't need the table. But if it's a rational inequality or quadratic or polynomial, yes, I recommend the table unless you know a shortcut. Okay, so what do I have to state? I have to state something, to find the domain of this function. Every time I'm asked to graph a function, I have to find its domain first. We didn't do that with e to the x because it's defined everywhere, but this function is not a friendly function. Yes, Mason, go ahead.
Oh, no, sorry.
If you
I was
want.
thinking,
You don't have to.
can't be negative.
I have to write something. I can say it can be 5 or it can be 3. I have to write something. What do I write?
X is greater than 1.
I have to write from scratch for everyone to see why am I writing it. So I heard something, but I was talking at the same time. So can you repeat? Anyone?
X not equal 1. Or X is greater than 1.
We have to go back to our lecture from last time. I know, I have yet to find one student who likes the square root. I haven't found that student. But I'm on strike right now. You have to tell me what I have to write, otherwise I will take a sip of water. Yes, Anna?
X minus 4 has to be greater than or equal to 0.
Was the shortest strike in the history of the world. Exactly. So the domain of this function is 4 to infinity. Please, I'm begging you to remember the domain of a radical function, please. Please. So knowing that, I start a table that starts at 4 and goes to infinity. It can't show anything else. And here I would like you to pick some numbers. But I would like us to pick some wise numbers. Because if you pick, for example, 7, 7 minus 4 is 3, the square root of 3 is 1.73. I really don't want to plot 1.73 plus 3. So come up with some numbers. Of course, you're going to come up with 4, and that will give us a
0.
very good. Of course, you're going to come up with 5. Why 5? Right, exactly. So then it gives me a 4. And I just would like you to come up with one more.
13.
13 minus 4 is 9. The square root of 9 is 3. 3 plus 3 is 6. Good enough. Is that okay? Perfect. So that's all we need. Yes, I would like to graph this function using transformations as well. Just real quick. So we have at 1, 2, 3, 1, 2, 3, 4. I forgot to ask you on the previous one. It's important to me. Can you please give me the range of this function? Sorry.
In parentheses, -3 to infinity.
Excellent. Indeed. -3 to infinity. Perfect. Okay, because I'm going to ask the same question here in a moment. So 5, 4. 6, 7, 8, 9, 10, 1, 2, 3, 6. So this is the graph of y equals the square root of x minus 4 plus 3. With transformations, you will say the base function is, by base I mean the original function, the simplest function that was used here is, of course. And then the first transformation will be the square root of x minus 4, and the second one will be a transformation on function 1, which will be the square root of x minus 4 plus 3. So what is the first transformation? What does the first transformation do on x?
Right.
Right 4, exactly. So from the square root of x, you will move to the right Oh, I think I graphed it at 3 instead of 4. I'm just going to insert one.
Yeah, you inversed it.
I'm sorry. I'm sorry. I did.
Yeah, you also went up 4.
4,
instead of
3. Oh my goodness. I did. Okay, sorry about that. But then the 5, 4 was okay. I should graph it one more time. Don't let me make any errors. So 1, 2, 3, 4. 1, 2, 3, right here. And then 5, 4. 6, 7, 8, 9, 10, and 1, 2, 3, and 6. Correct. So y equals the square root of x minus 4 plus 3. So then this would have been the square root of x, and this would have been the square root of x minus 4, and then up 3. And what about the range of this function? The range is right here. We cannot guess. 3 to positive infinity. The lowest y value is 3. The highest y value is infinity. Is that okay? Everyone? Yes? Perfect. Okay. Now we go to the natural log. And I think we got that natural log. Any questions from me? Stop me. Yes? Any questions? Okay, so we have y equals natural log of x minus 3. I have to find the domain of this function, and how do I do that? Can anyone tell us what we need to write? I can do 2 strikes in 1 hour. It's in your notes from last time.
X minus 3 is less than 0.
That would be in trouble, right? We would be in trouble because look at the graph of natural log.
Obviously greater than 0.
Exactly. Absolutely greater than 0. Log is not defined on 0 or negative. So then x minus 3 has to be greater than 0, x greater than 3. Domain of this function is 3 to infinity. So this is the simplest thing to do is just graph the base function. Here's the base function. It will always cross at 1, 0, natural log x. And now it's a function with a vertical asymptote at 0. And we have to shift it where? To the,
To the right.
yes, no, to the right. I was thinking, yes, indeed, to your right. Right 3. Good. What do I have to shift first?
Yes.
Yes. First I have to shift the asymptote. And my reference point, where does it go? From 1, 0, it goes to
4, 0.
Thank you. Indeed, 4, 0. So this point is 4, 0. And the graph of this function is natural log x minus 3. Domain is 3 to infinity, range all your numbers. Okay, moving on to, stop me if you have questions, of course, anytime. Now, piecewise defined functions are a major topic here. The other functions as well, but a piecewise defined function, so I'm going to copy f of x equals 1 minus x squared for x less than or equal to 0, and 2x plus 1 for x greater than 0. So there are several methods of graphing such a function. I'm going to show the method that I present in all my classes, which I think makes sense and it's easier than others, but I accept any method, and you can say I have a better one, and I'm fine with that. Okay. So first of all, I changed this into an interval. Can anyone give us the interval that replaces this? Excellent. Thank you very much. Can anyone give us the interval that changes this? Of course. Now I'm going to ask you what is the domain of this function.
Would be all the numbers.
Of course. Indeed, all your numbers, there is nothing missing. Excellent. Thank you, Mason. I'm sorry, Omari. Of course, thank you. My apologies. Okay. Obviously, 0 is a key point. Why is 0 a key point? Because it's like a threshold from one function to another. So at x equals 0, this function changes from this, which is what type?
Binomial.
Yes. Yes, a binomial, but it's quadratic. It's a quadratic function into a linear. Very good. So 0 is a key point. Now, in this case, I look at the symbol that I used for the interval. So on the left-hand side, right under 0, I will draw a bracket facing left. Right under 0, touching the bracket, I will draw a parenthesis. So see that these two symbols are exactly under 0, not to the left of 0, not to the right of 0, they're exactly underneath 0. Now I know this is an overkill, but I'm just making a point. These two branches may not be in the correct order, they may be reversed, who knows? Anything can happen. So can you tell me for the interval negative infinity 0, which function do I use?
Go quadrant.
Thank you. And of course, this is a silly question. If I'm using 1 minus x squared on negative infinity to 0, which function do I use for 0 to infinity? That is silly. Yes. Thank you for bearing with me. So now, on the left-hand side, it's quadratic. I'm going to plug in, let's say, -2 and -1. -1 mandatory because it's an X-intercept. And -2 because I like to have more than one point on the left. It's a quadratic function. Now, can we picture the graph just of 1 minus x squared? Yes, I can. It's x squared reflected up 1. But that's the entire function. I'm not going to graph the entire function here. I have to graph the function, that function between negative infinity and 0. But I just wanted to picture what's happening with 1 minus x squared minus x squared up 1. Okay, so let's plug in -2 and give me the y value. Let's plug in -1 and give me the y value. Let's plug in 0 and give me the y value. So when we plug in -2, we get, excellent. When we plug in -1, we get, as we should, 0. Thank you. When we plug in 0, what do we get?
1.
Excellent. Leave it alone for now. Now we're moving to the linear function. Please plug in 0. And you should say, of course not.
Not included.
Right. Bear with me and do it anyway. I'll explain why. So please plug in 0 on the right-hand side. Yes, luckily, it's also 1. I didn't mean it to be 1. So I'm going to give you another example because I want to show a gap. But it just happened. Or, if you want, let's change this into minus. Let's make the change, and I'll change it also here. Because I want to show a gap. That's more interesting. So, when we plug in, that will not change. So I have to make the change here. Okay, so not that the negative. So, I don't know, let's put 4. You're right. Forgotten we were putting in 0. Okay, so when I plug in 0, I get 4. Would you accept 4? Although you're not happy with the fact that I plugged in 0 on the right-hand side yet. right? Okay, in a moment we'll explain. So then it's a linear function, so I need to put in one more value. So when x is 1, then we get 6. So now let's graph what we see. So, very good. So -2, -3, -1, 0, and 0, 1. Remember the graph? So this is x squared, -x squared, and up 1. And this is a full point. Would you agree that this is a full point? Good, so here's the graph. It's quadratic. That's why I showed the graph of the entire function, in other words, 1 minus x squared. X squared, -x squared, and up 1. And now on the other side, we have 0, 4. So 0, 4 is here, 1, 2, 3, 4. And this is an open point. Why is it an open point? Because it's not included. If I don't leave it as an open point, or if I don't plug in 0 on the other side, I have to plug in 0.0000000001. Instead, I plug in 0 and I leave it open. So then when x is 1, y is 6, so the graph is this. So it goes from here up. We have the domain. I would like to determine the range. So this part, you'll see it quite often in chapter 2 and beyond. So when we determine limits, differentiability, etc., etc. So what is the range of this function? -∞ to 1 with a bracket, union. Yes? Yes, excellent. Do we understand why we leave it open? Do we understand why we still plug in 0 although we're not allowed to? Yes. Okay, moving on. Everything else okay here? Yes?
Actually,
Yes, Vicky?
why do we plug in 0 when we're not allowed to?
So if I don't plug in 0, I would have to start with the first number that I can think of on the right-hand side of 0. And the first number that comes to my mind is 0.000000000001. I don't want to plug in that number in there. So I'll say, okay, it gets closer and closer to 0, but it doesn't take 0. I can't start at 1, because if I start at 1, I have infinitely many real numbers between 0 and 1 that I will be losing or missing. So that's why I start at 0, leaving it open, because this point, 0, 4, does not exist. But I can't tell you what is the closest point to that.
Right.
I don't have it. I don't know what it is. So that's why I start with 0 and I leave it open. Better? Okay. Do we need to do number 10? If you say no, we move on. If you say yes, we'll do it.
Yes.
Okay, very good. So that's function composition, extremely important for the chain rule. So here we have a function which is f of x, which is 2x minus 5, and g of x, which is -3x squared minus 2x plus 4. And we're asked to find f cum g of x. Okay. I would like to add here g cum f as well. So what does this mean? It's one of the 5 different ways of determining new functions. We can add, function, subtract, multiply, or divide. Given 2 functions, we can use these operations to create new functions. And this is the 5th method, function composition. In function composition, we basically replace one function. We replace x by another function in the first one. So this is the inner. How do I know? Because it's the first one applied to x. So that's why this is f of g of x. So this is the inner function, and this is the outer function. So then I have to start with the inner and replace it. I'm going to continue here and replace in f. I replace x by g. So I'd like to stop here for a second and discuss and tell you what I see when I look at f. When I look at f, I see this. You have to see the pattern. So the pattern of f says to me that 2 times whatever you want minus 5. So this is what I want now. This is my whatever I want, the negative 3x squared minus 2x plus 4. So if this is negative 3x squared minus 2x plus 4, this must be negative 3x squared minus 2x plus 4. So then, this is 2 multiplied by negative 3x squared minus 2x plus 4 and minus 5. Let me know if this is understood. It's okay if you say no. Is this okay? So now I have to distribute 2 and combine like terms. And then look at the other one. So negative 2, negative 6x squared minus 4x plus 8 minus 3, which is 3. You know what I mean. Plus 8 minus 5, which is 3. So this is the function composition of f comma g. Now, when I determine g comma f of x, I have this time g of f of x, which is g of 2x minus 5. Let's go back to g for a second. What does g tell me? G says this to me. G says g of whatever, really, literally whatever, is negative 3 times that whatever squared, and minus 2 times that whatever and plus 4. I just want to plug it in. So negative 3, the whatever to the second power minus 2 times the whatever and plus 4. When we look at functions, this is what we have to see. We have to see their pattern so we can easily evaluate them for anything. Any questions so far before we finalize this? I cannot leave it like that. I have to square and I have to multiply by negative 3. I have to distribute negative 2, blah, blah, blah. So how many terms do we get? That's why we discussed that at the very beginning. How many terms do I get when I square 2x minus 5? Okay. Mason already gave 3. Okay, so the first term squared. 4x squared minus 2. Keep in mind there was a 2. Multiply these 2 first. You get negative 10 times 2, negative 20x. Because there are 2 terms identical, right? That's why I multiply by 2. So minus 20x and plus 25. And then I distribute minus 4x plus 10 and plus 4. And then I get negative 12x squared and plus 60x. I think
75.
it's 75 and minus 4x and plus 14. Thank you very much. And negative 12x squared, and I think that this is plus 56x, and this is negative, is it 61? Correct my mistakes at any point in time. And even if you're wrong, I'd rather go back and check if there is any doubt. So this is the function composition of g comma f. Okay, now we want to decompose. Any questions? In the next a problem we want to decompose. So we're given f of x equals I would like us to determine an inner, let's call it g of x, and an outer, let's call it f of x. There's an e here, sorry. So give me a function that is the inner and a function that is the outer. Can you use more than, can you have more than one correct answer? Yes. Can you use more than one function? Yes. But I only need two. Yes. Omar?
Here's 2x minus 4.
Excellent. We selected inner to be 2x minus 4. That's perfect. And what about the outer?
1 over, I don't know what it's called.
Very good. Awesome. Indeed. 1 over the absolute value of x. So once we determine a value for this, then we have to apply 1 over the absolute value of x to get the final answer. Does it make sense? Okay. Moving on. Let me know if you have questions, please.
Why is the,
Yes?
The 1 over the absolute value of x?
Yes?
Oh, never mind.
You sure? Do you want me to show the function composition?
Yes, please.
Perfect. So according to this, we claim that f comp g of x is f of x. So we want to show that. So f comp g of x is f of g of x, correct? Which is f of 2x minus 4, correct so far? But f is 1 over the absolute value of whatever. And we got the function back. Is that better? Everyone? Yes? Perfect. Okay. Moving on. This is a crucial topic. Once we understand the difference quotient, then we can build on it in the entire course, literally. The entire course is based on the difference quotient. For different functions, of course. What type of function is this? Perfect, quadratic function, quadratic. The difference quotient is given to us today, but we will have to, moving forward, we will have to remember what it is. Now, since we are here, I'd like to explain what it is. So, everyone understands, or maybe you forgot what it represents. So, let's talk about it. So, let's say I have a function. This is f of x. And I have 2 points that are on the function. I'm going to call them a and b. And point A has coordinates x, help.
F of x.
Thank you very much.
I watched it last.
So there are no surprises. Awesome. And this point is extremely close to the first point. Very close. But imagine that I'm zooming in so I can explain what I'm doing. Because if that point is here, I'm not going to be able to explain anything. But they're very, very close. So close that I say the x-coordinate of b is x plus a little bit. Tiny bit. Maybe it's 0.01. And you can say, is this 0.01? Of course not. I'm just zooming in so I can explain. So now I need the y-coordinate of this point, please.
F with x plus.
Of course. No surprises there. Good. So I'm going to draw a line. It's called, has nothing to do with trig. It's called a secant line, AB. The secant line AB crosses the graph of the function in 2 points. It's not a tangent. A tangent will, at this point, let's say at point C, a tangent will look like this. But AB is a secant line. It has nothing to do with trig. It just crosses the graph of a function in 2 points instead of 1. Okay, so I would like to determine the slope of the secant line AB. By the way, what will that represent? It will represent the rate of change of function f of x between Between what? Of course. That's exactly what it will represent. So let's think about this for one more moment. I have a function. I have 2 points. They're extremely close to each other. So close that the x-coordinate of the first one is x and the x-coordinate of the second one is x plus tiny bit. So they're very close. And now I would like to determine the slope of the line passing through these 2 points, which is basically the rate of change of the function between these 2 points. And since they're so close, we're gonna put an operator in front of this. We're gonna put an operator in here that will give us the slope of the tangent line at A. But we don't have that operator just yet. So now, the rate of change between A and B, how do I write that? Can anyone dictate? Which is nothing else but the slope of this line. Yes, I'm ready.
Y2 minus Y1 over
Perfect.
X2 minus X1.
Right, but I would like to use, it's excellent. But I would like to use this notation. Excellent, everything you said is perfect, but I like to use the notation.
F
Yes?
x plus h.
Yes, f of x plus h, very good. Minus?
F of x.
Indeed. So that's the numerator. F of x plus h minus f of x over?
X plus h minus x.
Of course, thank you. Which is indeed, Omar is perfectly correct. He said y2 minus y1 over x2 minus x1. And that's how we determine the slope of a line passing through the 2 points. Absolutely. Okay, so now, of course, these two go away. So we're left with this. And this is the difference quotient for any function. And it was given to us in this problem, but moving forward, we have to remember it. Any questions? One more time, what does it represent? Is the rate of change of this function between 2 points. But they're so close that later on, we're going to do something interesting with this definition. Okay, so we're asked to determine this rate of change between those points A and B for this function. So the function, I'm going to copy it here. Negative 2x squared plus 3x minus 1. And of course, I would like you to practice between now and Thursday all types of functions. I have a lot of examples last time, or if you want me to show other examples, I will, of course. So radical functions, rational functions, linear functions, cubic functions, anything. Okay, we have plenty of examples. Okay, so in order to determine the difference quotient for this function, I write it again. Which of these 3 pieces I have and which I don't, and I have to work on.
The x is not h's, right?
Yeah, the F of X.
I have the f of x. Mason, what did you say?
Like, we have, yeah, I guess that's x in a sense.
I have f of x, yes.
You don't.
But you plug in for the x, so you leave the h. Correct.
So let me repeat the question. I see one piece, I see the second piece, and I see the third piece. Out of these 3 pieces, which ones do I have and which ones I have to work on?
You have F of X.
I have f of x, agreed.
You do not have H.
I can't. It's a tiny number. I don't care.
Does that mean you do or don't have it?
I don't care. I can change it. I can determine. It's a tiny number. Whatever it is, whatever you give me, it's fine. I can determine that.
But then we have to work on f of x plus h.
Of course, I don't have it. Of course. This is done. This is done. I can't do anything to those 2 quantities, but f of x plus h I don't have. So I'm going to continue with f of x plus h here. We are looking at the function. We see the pattern. And now you will tell me what to write.
Maybe 2 times x plus h squared
Excellent.
plus 3.
Okay, do we agree with this? We just did that, right? with function composition, sort of, right? So for f of x, we plugged in x plus h. Good. So how many terms do I get when I square x plus h? That's one of the reasons, there are many reasons, but that's one of the reasons why I show that those three special products from day one, because they would pop up at least twice or three times every class. And if we can avoid discussing those three, we are in business. Okay, very good. I'm ready.
X squared. Yep, x squared. 2x h.
Excellent.
And then h squared.
Excellent. Thank you. The reason why I put, some students ask me, why do you put equal symbol here and equal symbol here? So that I know that there's something that follows. If I don't put something here, you may not look at the next row. It's up to you. You don't have to. It's a matter of habit. Okay, now I have all three pieces. I can put everything together. So before we simplify this difference quotient, I have two remarks to make. Every time we determine the difference quotient for any function, any type of function, anything you want, two things must happen. One, all terms without h from the numerator have to go away. The difference quotient is a ratio. For any function, it will be this ratio. So when you're done with the top, simplifying everything, all terms that do not have h must simplify at the top. That's the first thing that has to happen. The second thing that has to happen, the h in the denominator must go away. Somehow. I don't care how. You cannot erase it. You have to show how and why, right? But this h must go away. Will there still be an h left in the problem in this final answer? Yes. Yes, but not that one. So let me repeat. Two things must happen for any function when I determine the difference quotient. The first one is, at the top, all terms without h have to cancel each other. Cancel, go away, whatever. And the second thing that has to happen, h in the denominator has to go away somehow. If these two things do not happen, something is terribly wrong. Okay, ready? So now I will continue from here. You will learn very soon that I always run out of room. So that's no exception, of course. So instead of this, I'm going to put all this, negative 2x squared minus 4xh minus 2h squared plus 3x plus 3h minus 1. I'm going to put the h in the denominator as expected. And now I would like you to distribute negative 1 to the function and tell me what to write.
Plus 2x squared minus 3x plus 1.
Excellent. Perfect. Thank you very much. Okay, now, what did we say has to happen? First step, that has to happen. Otherwise, I can't continue.
All
Terms. All terms that do not have h must go away. It's a bonus if some terms with h go away. That's fine too. But definitely all terms without h have to go away. All terms without h went away. Now, how many remaining terms we have? They all have to have h in common because eventually the h in the denominator has to go away. And it will only go away when I factor out an h from the top. So that's the second thing that has to happen. Which is?
Negative 2h minus 4x plus 3.
Yeah, she gave me in a different order. That's no, it doesn't matter. It's the same thing. I like to put x first because it's a function, but it doesn't matter. So do we all understand why we have a negative 4x minus 2h plus 3 at the top? Is that okay, everyone? So then the final answer is negative 4x minus 2h n plus 3, and it's done. And you can say, and how is this the rate of change of a function, blah, 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 between 2 points? It is. And you'll see why in the next chapter. Okay. This is another crucial type of problem, factoring. Any questions on the previous one? It's another very important type of problem to simplify this by factoring. So let's do that. Just give me one.